Now here is a question for us. Show that P is equal to 1 over 3 rho c squared is dimensionally correct and the symbols maintain their usual meaning. Now we have this as P. P is actually the pressure of the gas. In this case, we're actually considering a system of gases. Now we have this symbol. This symbol stands for the density of the gas. Now see here, that stands for the velocity of the motion of the gas. So we need to show that this formula is correct. And the symbols will maintain their usual meaning. So we have all these symbols being exactly what you know them to be initially. And the first thing we need to do, we need to draw out a cubical vessel. And we're going to say that that cubical vessel actually contains some gases. So I'm going to use this part. And we have this. So this is the cube. We got this and this. So let us say this is the y-axis. And let us call this the z-axis. So this is going to be the z-axis. Well, let me call this the x-axis rather. And then we're going to make this to be the z-axis. So let us say this is the z-axis. Now, this is a cube. Let us say this is one face. And if we wrang out this face, we're actually going to find that there is a face that faces this face. So let us say this is face A. And there is a face at this position behind, which is actually facing face A. So we're going to call that face A prime. So I'm just going to write that over here. That will be face A prime. That is a face behind that face. I don't really know how to show it. Hopefully you understand the point. Now let us say this other face is face B. And so there is also a face that faces it behind at this position. So we're going to call that face B prime. And let us pick out another face, which is this. So that is face C. Now as usual, we also have a face under this, which is actually facing the face C. So we're going to call that face C prime. Now, let's say this is the origin of this Cartesian plane. Now, if we picked out a molecule with mass m, and it's moving in the x-axis, or in the direction of the x-plane, we're going to find that this molecule would have a velocity. So let us say that velocity is written as v sub x. That will be the velocity for that molecule in the x-axis. Now, what if the molecule moved in the z-axis? What is going to be the velocity? That will be v sub z. What is going to be the velocity in the y-axis? That is going to be v sub y. Now, these three velocities can actually be related. There is a formula that relates these three velocities. That is going to be written as c bar squared, and that is equal to vx squared plus vy squared plus vz squared. So that is what you have. Hold that at the back, because we're actually going to use it in the future. That is in the nearest future in the same video. Now, let us take one molecule which is moving in the x direction or the x-axis. We're going to find that that molecule obviously will strike upon the B face. That is this face. So as it strikes it, there is going to be an amount of momentum that will be dissipated or created. So that is going to be mvx. This will be the momentum with which that molecule is going to strike this face B. But you need to know that gases, they actually take part in an elastic collision. So that should be elastic. What that means is upon striking this, you're going to have the momentum conserved, and virtually that gas would move away from here. So it's actually going to move back toward the other face, which is B prime. And as it moves away, it's actually going to move with an amount of a momentum, and that's going to strike this other part. So as it strikes this part, we're going to have another amount of momentum, which in this case, I'm going to say we have it as minus mvx. So there is actually two momentums because we have the gas bouncing away from the phase B and rebounding from there, moving away from there to the phase B prime. And so these are actually going to be the two momentums which would be accompanied with that gas molecule. What then is going to be the change in momentum for this process? How are you going to find it? So if you talk about the change in momentum, in that case, I'm going to write it as dp. That is going to be this minus this. So you would have mvx minus negative mvx. So now we're going to have dp, which is the change in the momentum. Remember, this is supposed to be in the x-axis. So we would have a mvx plus mvx. So that actually gives us 2mvx. So I need to write it in small form. That is what you're going to have for the change in momentum in the x-axis. Now, there is something else we need to understand. We know that the length of this cubical vessel is actually L. We're just going to designate that as L. So we got L here. Now, we know that as the molecule moves from the origin toward the B face, that actually covered a distance of L. And we're also going to have the rebound of the molecule away from the B phase to the B prime phase. And so that is going to follow another distance L. And so there is actually going to be a distance or a displacement of 2L. That will be the total distance covered within this change in momentum. Now, why do we need that? We know that velocity, in this case, in the x-axis, is actually going to be the displacement divided by the time. Now, we need to make the time as a subject. If we made time as a subject, that is going to be displacement divided by v sub x. But we know that the displacement is 2L. That is the molecule moved in two separate directions. So that is going to be 2L divided by v sub x. So that is what you're going to have over there. Now, I'm just going to wipe up these out because by now, hopefully, you understand the point already. So we are going to have the change in the momentum in that axis to be equal to 2mvx. And then we also have the velocity, or the time rather, in this case, that is equal to 2L divided by v sub x. So that is what you're going to have. Now, we know that from the Newton's second law of motion, we have that the change in momentum with respect to time is actually equal to the force that was required for the motion. So first off, we need to find what is going to be the rate of change with respect to time. So let us work the right hand side of the equation first of all. So I'm going to wipe these out. I would also wipe these out. Hopefully you can recall. So we have that the change in the momentum. So this is change in momentum. And that should be taken with respect to unit time. We know that is going to be dpx divided by t. So we know dpx is equal to 2mvx. This is divided by 2L divided by v sub x. Now we know this is going to go to this other side. So this will become 2m sub x multiplied by another v sub x. And then you're going to have a 2L here. So we know this 2 is going to cancel out. So that would give us something like this. We should have, just going to take these out. So we're going to have something like this. That will be mvx squared, and that is divided by L. Bear in mind, this is the change in the momentum with respect to time, this stuff. So we're going to keep it in one place. Now, I'm going to wipe these out. So we have the change in momentum with respect to time in the x direction, or x-axis. That is mv sub x L. So that is what we have. Now, what is the next thing that I need to do over here? What is going to be the next step? Now, you need to understand that this is a change in the momentum that will occur at one side of the cube. So at the B part and the B prime part. So from this part, you're actually going to have one of this. But you also have the change in the momentum with respect to B prime. Now this would only stand for one side. So you need to add this with itself to create the change in the momentum with respect to x, with respect to the B prime. That is the other side. So this should be 2 of it. So I'm just going to say that is the total change in the momentum with respect to the x direction over time. So let us write it that way. So the total momentum in the x-axis, that is not just going to be with respect to one face, but the 2 faces. So I'm just going to take these out. In the x-axis, or should I actually say in the x direction, that is going to be total. So I'm going to write it as a mp, well, dp sub t, and that will be 2 multiplied by dp sub x divided by t. I know that should happen because that is pretty much the same thing. The thing that would happen on one face of the cube, that is the same thing that would happen on the other side. So this is going to be 2 mv x squared divided by L. Now buried at the back, this would actually be the total momentum in the x direction. So I might well still write this as dp sub x. So this should be sub x t. And so that is equal to 2m vx squared divided by L. Now what is going to be the total of changing momentum with respect to all directions? So let us write it in the y direction. So in the y direction, that should come off pretty simple. This will be vy squared and divided by L. If you wanted to have it in the z-axis, that is going to be the change in the momentum with respect to the x direction. Well, in this case, the z direction. And that is going to be 2m vz squared divided by L. So now we want to find out what is going to be the complete total momentum with respect to each direction, totally. Okay, so let us find that. So that is x, y, and z. And that should be a total. So that is going to be 2m vx squared divided by L plus 2m vy squared divided by L plus 2m vz squared, and this is divided by L. Now we know this is going to be equal to 2m divided by L, and we're going to have vx squared. So I need to write that better. This is Vy squared. And here we're going to have Vz squared. Now we already know that this is equal to bar C squared. We had already said that. So this whole stuff, this should be bar C squared. Feel free to rewind the video and go back to where we actually said that. So with this, I'm going to say that the total change in the momentum with respect to all axes, that will be equal to, well, I feel there is no space down here. Let's do it over here. Whoa. So this is dp, this is x, y, and z. That is in the total case. So this should be 2m bar c squared divided by L. So that is what you got. Now remember, we actually had this as the change in momentum with respect to time. We had already done that. So we know that from the Newton's second law of motion, you have it that the change in the momentum with respect to time is actually equal to the force. And this stuff, this is equal to dp in the x-axis and the y and the z-axis. This was completely what we found. So we know that F is exactly going to be, summation of dp in the x, y, and the z-axis in total form. We had already gotten that. That was equal to this, right? So that is what we're going to do. So this is going to be equal to 2m bar c squared divided by L. Now we know that pressure is equal to force divided by area. We're going to change this force to the pressure. Now if you cross multiply with this, you would have that the force is equal to the pressure multiplied by the area. So that means we actually have the force be equal to P multiplied by A, and this is equal to 2m bar c squared divided by L. Now I can take this to this side, and this is going to be P is equal to mc bar squared divided by A multiplied by L. Now we know that the volume of a cube, which is written as V, is the same thing as the area multiplied by L. So in this case, I'm going to change AL and substitute it with V. So this is equal to mc bar squared, and this is divided by V. Now what is V? V is the volume of the cube. So what is the volume of the cube? What is it going to be? We know that the volume of a cube should be 6L raised to the power of 3. So in this case, I'm going to have P, and that will be equal to mc bar squared divided by 6L cubed, right? So we know 2 can cancel here and make it 3 below. So that means we have P is equal to mc bar squared. Well, that should be divided by 3L cubed. So I'm actually going to rewrite this, and I will take it to this form. So P will be equal to a third of this stuff, mc bar squared divided by L cubed. Now what is L cubed? We know that L cubed is going to be the volume of a surface, because here we're going to have meter cube as the unit of this operation. So that gives us a volume. So I'm going to change it. We would have this be equal to 1 over 3. And here we're going to have m multiplied by c bar squared divided by v. Okay? So let us expand that expression. We have P, and that is equal to 1 over 3 multiplied by M divided by V. And this is multiplied by C bar squared. Now we already know that the density of a material is actually the mass of the material divided by the volume. So in this case, we're going to take M over V, and we're actually going to replace it with the rho, which is actually the symbol for density. So that means we have P, the pressure, that is equal to 1 over 3 multiplied by rho, and this is going to be multiplied by C bar squared. This is exactly what we were actually asked to find. We were actually asked to derive this. Now, how can you find whether or not you have the dimensions of this to be correct? How would you tell that? So let us try to do that quickly. We know that pressure is equal to the force divided by the area. Now, force is the mass of a molecule or a substance multiplied by the acceleration. This is divided by the area. Now, what is acceleration? Acceleration is the velocity of a substance or an object which is moving with respect to whichever direction. And that is the velocity divided by time. This is going to be divided by the area. Now, we know that the dimension for mass is actually written as m. And we know that the dimension for velocity, that is going to be m. So that should be mt. Well, not mt. That is lt. So this is lt raised to the power of -1. And this whole stuff is divided by t. This is all divided by the area, which has a dimension of L squared. Now here we can actually take this up and make it to be T to the -2. So pressure, that is equal to mass multiplied by LT raised to the power of -2, and this is divided by L squared. Now we know that L can cancel 1 out, and you would have pressure with its dimensions being this way. So this is going to be L raised to the power of -1, and here we have T raised to the power of -2. What we did is take L up, and that produced the power of a -1, as you can see here. So this is going to be the dimension for our pressure. Next up, we're going to find what is going to be the dimensions for the other side. And so if we find it to be equal to this side, which is on the left, we're going to say this is dimensionally correct. So here we have density, and we also have the velocity. The velocity is actually squared. So what is density? Density is equal to mass divided by the volume. Now mass has a dimension of m, and v, which is the volume, has a dimension of L cubed. Okay? So this is going to be ml raised to the power of a -3. And then we have c. We know c is actually velocity. So therefore, if we have c squared, that is going to be v squared. Now v itself is actually lt raised to the power of -1. That is the displacement divided by time. So v squared is going to be lt raised to the power of 1 squared. So let us take this out. So here we're going to find that v squared, which is the same thing as c bar squared. That is going to be equal to L squared multiplied by T raised to the power of -2. That is if we expanded this bracket with the power. Now we have V squared or C bar squared multiplied by rho squared. So let us try to write that out. We had rho. Well, rho is not supposed to be squared. This is ml raised to the power of -3. So we actually have to combine this stuff. So I'm gonna wipe this stuff out. Now we have rho c bar squared. So let us see what that is gonna be. We're not actually gonna consider this. That is actually constant. It's a normal number. It doesn't have no dimension, so we're not bothering ourselves with that. So we actually have the rule, which is m multiplied by L raised to the power of negative 3. And this is now multiplied by L raised to the power of 2. And we have T raised to the power of negative 2. Now if we combine these stuffs, you would actually find that we have a negative 3 plus 2. That is going to give us a negative 1. And here we have negative 2. And so you have a rho. Well, that should be rho C bar squared. So I'm just going to write it down here. This is equal to ml raised to the power of negative 1 t raised to the power of negative 2. This is what we have for the second one. Now as you can see, we have that this is completely the same as this other one. So we are correct. This equation is actually dimensionally correct. And how to derive it, we have also shown that. So hopefully you understand the video. Make sure you subscribe and press the notification button, and or always visiting my channel. Do have a nice day.